Including this session is on one-shot signatures, quantum versus classical binding and obfuscation permutations, and Omri Shmueli will give the talk.
Okay, so this is a joint work with Mark Zandri. And in this talk, we will see connections between three areas of cryptography. The first one is quantum cryptography, which are schemes that use quantum mechanics in the scheme for the benefit of cryptography. The second is what we usually call post-quantum cryptography. These are classical schemes that stay secure even if the adversary has a quantum computer. And the third one is classical cryptography, does not take into consideration any quantum information. Okay, so specifically, we will talk about this quantum object called one-shot signatures. Its connection to classical commitments that are secure against quantum computers, and the purely classical question of, is it possible to obfuscate the circuits of pseudo-random permutations, for example, using indistinguishability obfuscation, and then making the circuit public? Okay, so I would like to start with this question. Is it possible to construct a one-time signature token? So I'm going to have this generator. It's going to sample a verification and signing keys. And given an arbitrary message M, when I sign, the signing process is going to somehow consume the signing key and destroy it uncontrollably, even though I held like a copy of it before. And we don't need to think too much about it. In the world of classical information theory, that's clearly impossible. Why? Because if I sample this token and the signing key is classical, I can keep a copy on the side. And when I want to sign M1, I can sign it. And even if the signing key is going to get lost or destroyed during this process, I held the token on the side and I can use it again and again. Okay, so this stops being true in quantum information theory. Because one thing that we know in quantum information theory is that if I want to extract classical information about quantum state that I don't know nothing about, I'm going to lose something. So if I have this quantum state psi, so when I process it, I'm going to learn something. I'm going to learn some classical string S, but it might degrade my state or even destroy it. It's going to change irreversibly. That's the point. And this is actually the source of a lot of pain in quantum algorithms. A lot of formal impossibility results follow exactly from this, but this is our usual paradigm in crypto, right? We take algorithmic barriers, we try to use them to our advantage. Specifically, we want to make this degradation of the quantum state inherent for the benefit of quantum cryptography. And this led to this idea of one-shot signatures by Amos, Giorgio, Chiares, and Zandri from 2020. You can think of one abstraction of one-shot signatures as follows. So I'm going to have this box. And every time that I'm executing this box, this is a quantum algorithm, and everyone has access to this quantum algorithm. And every time that I push the button, I'm going to get a sample of a digital signature pair of verification and signing keys, and the signing key is going to be quantum. And every time that I'm using this pair, the signing key is going to self-destruct magically. So I can do it many times. I can sample many fresh pairs with high probability. In particular, the verification keys are going to be different, right? This is just behaves like a digital signature scheme. And now I want to sign. So given an arbitrary classical message M and the quantum signing key, when I sign, poof, it magically gets deleted, even though I held a copy of the signing key before. That's the point. And what do I mean formally by this like self-destructing quantum signing keys? So if I have a quantum polynomial time adversary, and this adversary has access to the box like everyone else because it's public, it cannot use the same key twice. What do I mean by this? So this is going to be possible. Just I'm going to use the box many times to generate all of these pairs. Another thing that's going to be possible is generating many different verification keys with many different messages and corresponding signatures. what's going to be hard is finding two different signatures for the same verification key using two different messages. So you can think of it as a collision in the verification key for two different messages and corresponding signatures for these messages. And in particular, if we know that this is computationally intractable, I cannot use the quantum signing key twice, right? Because it was sampled with the verification key. If I used it to sign two different messages, I got exactly this. Okay, so this is kind of a simple object, but it turns out that it has a lot of power. For example, we know that it solves all of these open problems in the field of decentralization. Yeah, I'm not going to have actual time to go over them, but there is actually a very nice video by Justin Drake touching on some of the applications for blockchains. And another thing that we know how to do is quantum cryptography with classical communication. And when I say quantum cryptography, I mean quantum cryptography that we know that we cannot do using only classical information theory. And if you have one-shot signatures, you can execute this cryptography in a model where you have only like quantum local computers, and they all communicate using the already existing, essentially, classical communication infrastructure. Okay, so my point is that for all of these applications, we don't know of any primitive in even quantum cryptography that can give us any of them. Okay, so we have some motivation for constructing them. What do we know in terms of construction? So in terms of standard model constructions, we don't know anything, not even under non-standard assumptions. And in that same work that defined one-shot signatures by AGKZ, a classical Oracle model construction was suggested. The security proof was found to contain this fatal bug, and we don't know the status of the security of this construction from 2020. Okay, so we actually have one paradigm for constructing one-shot signatures. It is based on this object with original motivation actually coming from post-quantum cryptography. So we're going to do a detour into post-quantum cryptography and learn about this object, which is a variant of a collision-resistant hash function. Okay, so this starts with this work from 2015 by Dominic Unruh, basically observing that if I have a classical commitment scheme, and this commitment scheme is going to be post-quantum computationally binding, it is still insecure in some intuitive sense, let's say. And that's something a bit strange to say, because I just said that it's computationally binding. And before explaining what I mean, what Unruh showed that this follows from the same thing actually happening for hash functions. So if I have a post-quantum secure collision-resistant hash function, it is still maybe insecure in some intuitive sense against quantum computers. So let's explain. This is a post-quantum collision-resistant hash H. It is computationally hard for a quantum polynomial time algorithm to get a colliding pair. And if I'm using H in the context of commitments, what I want is essentially this, right? If I'm using it in an interactive protocol, when I'm giving you Y and Y some image of H, it should fix the pre-image X. So I shouldn't be able to send you Y and then, for example, choose between X0 and X1. And the point is that if we're thinking of a classical committer, a classical adversary, that's going to be equivalent. So if I have a hash functions that collision resistant, I know that I also have this property here, and I can use it for commitments. And the reason is rewinding. This is a very famous technique for analysis of protocols in the classical setting. And I'm going to be able to rewind the adversary back and forth during the protocol to get a collision, if it can do this. So now we're thinking about quantum computers. And the point is that this equivalence is no longer true. And the reason is essentially the same. It's, again, rewinding, but in the other direction. We actually don't know how to generally rewind a quantum computer. And we also know that quantum rewinding is hard. We have a lot of people over many years working on trying to understand when can we rewind the quantum computer and when we cannot. But let's be more concrete here. I want to ask what can a quantum computer actually do in this specific situation with the hash function h. So I'm going to try to use minimal quantumness here, but I'm going to start with uniform superposition of all of the possible inputs to h. Then I'm going to compute h in the forward direction, and I'm going to measure the output register of h. So what we know by basic quantum mechanics is the quantum register that contained the superposition of the input is now collapsed to this uniform superposition of all of the x's that reach y in h. And I can give you now the quantum adversary, I can give you this y as the commitment, but the point is that now I'm holding this superposition of all of the x's. And maybe I have this efficient quantum algorithm that can take this superposition and steer it to a specific x, for example, that starts with 0, even though I don't know what this superposition looks like. And in particular, this means that I chose something with respect to my pre-image x. Okay, so this same work by Dominic defined this stronger notion, logically stronger than collision resistance. He called it collapsing, and intuitively and almost formally, if I have an H that's collapsing, what we're going to have is that this superposition is going to be indistinguishable from a collapsed state, essentially. Like this classical distribution on the right is just means I measured the superposition of the x's. And for collapsing hash functions, we have plenty of constructions. We have a year later by Unruh again, based on LWE, and a bunch of other works showing it from SIS. So it's well established that we have collapsing hash functions. And this left this question unsolved for a while. So do we have a non-collapsing collision-resistant hash? And we have two options, essentially. If we don't have one, it means that somehow I can show that every collision-resistant hash function is also collapsing. So somehow I lose the superposition immediately. Or we do have hash functions that are collision-resistant, but you can actually observe the superposition of pre-images. Let's be more concrete, okay? So what is a non-collapsing and always non-collapsing CRH? It's given by two algorithms, a classical algorithm and a quantum algorithm. H is just a CRH, just plain old collision-resistant hash. And D is a efficient quantum algorithm that can detect superpositions of inputs to H. So again, if I'm starting with a uniform superposition, I'm going to compute it forward and measure Y. I'm going to be able to detect the quantum superposition. So D can actually tell the difference between a superposition of images and just a classical sample from like a uniform sample from the pre-image set. I'm simplifying the definition a little bit, but this is the main intuition behind this definition. Okay, so yeah, the motivation initially came from understanding post-quantum cryptography. But then a few years later, something remarkable happened. We found out, Mark Zandri showed, that this object exactly is also a very powerful object for quantum cryptography, when the scheme actually wants to use quantum mechanics. In particular, Mark showed that if you have a non-collapsing CRH, you can construct this more powerful object called quantum lightning, which is stronger than public key quantum money. And then a few years later, we also known by AGKZ and Dall'Agnolo-Spooner that non-collapsing CRH gives us one-shot signature, which is even stronger than quantum lightning. And we also know that if you have a non-collapsing CRH, then these notions of classical and quantum bindings are inherently not the same. The definitions are not equivalent. And we had this picture. So we know that if we have a non-collapsing CRH, we have all of these powerful objects. And the point is that if I'm looking at the top floor, we have classical oracle constructions. Sometimes we even have standard model constructions. And in the bottom floor of this figure, we don't have almost anything. Okay, so what we show is that you can actually, relative to a classical oracle, construct a non-collapsing CRH unconditionally. And if we move to the standard model, you can assume the quantum polynomial hardness of LWE, sub-exponential noise to modulus ratio, sub-exponentially hard one-way functions, and sub-exponentially hard indistinguishability obfuscation for classical circuits. You can get a non-collapsing CRH in the standard model. And I'm going to focus just on the intuition of getting the top part for the time that I have. Okay, so let's gather some intuition for how to construct a non-collapsing collision-resistant hash function. Essentially, all I want is a hash that's going to be collision-resistant, but these two things are going to be computationally distinguishable by an efficient quantum algorithm, efficient and public. It must be able to do this without any trapdoor. And the point, again, this is going to be very, very intuitive. The point is that the challenge, if you want non-collapsing, what we really want to do is to publicly verify a quantum state without revealing the description of the quantum state. Why? Because my quantum state is going to be this superposition over all of the pre-images to some y in H. And the description of this state in particular includes the subset, and the subset includes the collision. So I must be able to verify this quantum state publicly without telling you what it looks like. And for these kind of states, we actually know that we know how to do this essentially only where the superposition over the set contains a lot of structure, again, intuitively. And what we know about collision resistance is that it actually needs to lack structure. So if I'm giving you an X and a Y, and I know that X goes to Y, this lack of structure in H is exactly what avoids me from coming up with a new X prime that also reaches Y. Intuitively, again, I cannot be too formal here. Okay, so what we show in a nutshell is that if you have a random permutation, it is exactly going to be the object that mediates these two needs. So it can create unstructured collision-resistant sets, and it can also move these unstructured sets into structured sets that then we are able to verify publicly the superposition of the set. A little bit more specifically, we have a random permutation pi, and I'm going to define these two functions, h and j, which are just the first and last output, n/2 output bits of pi. Okay, so here is one simple fact, right? If I'm having this random permutation pi, and I'm looking on the output as the first n/2 bits of pi, this is just going to be a random function from 2 to the n/2 to 1. Right? And we know that this function can be very easily proven to be collision resistant. And now I want to verify, I did this superposition and I measured, and I have this superposition of pre-images of H. And now I want to measure that I actually have a quantum superposition and not just a classical state. Okay, so in a nutshell, what you can do is to do this process for H. And then given Y, which is the output that I measured, I can sample this IID random subspace SY. And SY is going to be this sparse subspace. Sparse, formally, you can think of it as a random subspace that takes a negligible fraction out of the full space that it lives in. But it's going to be structured, that's the point. And then what I can do, so if I'm looking at the pre-image set of Y, it's going to be a highly unstructured set. But if I'm looking at the J values, the J values is a very structured set, right? This is just like all of the strings, binary strings of length n/2. And now we can think of it as an algebraic object as vectors over Z2 in length n/2. And if I have this full set of vectors, I can now think of them as coordinates vectors for this subspace SY. So what we show in our work is how to move from this unstructured pre-image set of Y to this structured set SY. So we move the superposition of pre-images to a superposition over the secret subspace SY. And the point is that these are things, at this point, we just have things that we already know how to do. For example, by Aronson and Cristiano from 2012, you can quantumly verify efficiently this superposition without revealing the description of SY. And that's important. I cannot tell you what SY looks like because I can go back and forward, and then I would find a collision. So this we already know how to verify publicly, this superposition. Yeah, and there are a lot of things here that I definitely skipped over. So in the paper, we show how to formalize this. Okay, so I briefly showed you connection between two things, this one-shot signatures, this quantum object, and this discrepancy between classical and quantum notions in post-quantum cryptography. And what about the classical part? So the classical part comes when I actually want to prove the security in the standard model. And we just use a random permutation. So in the actual scheme in the standard model, I'm going to use a pseudo-random permutation pi, and I'm going to obfuscate it using indistinguishability obfuscation. And then I'm going to publicize all of these circuits after obfuscating them with I/O. And if we think about it for a moment, that actually needs to deal with an older problem of how to take, because I'm taking a PRP and I'm going to obfuscate it and publicizing the circuit. And that was an open problem for at least a decade, whether you can do it and still hide the information of the PRP. And we defined this new object. It's called permutable PRPs. You can intuitively think about it as an analog of puncturable PRFs. This is one way to think about it. And one thing that it lets you to do is to give you this indistinguishability on the bottom. So if I'm sampling the PRP randomly and I'm going to obfuscate it, this is going to be computationally indistinguishable from doing the same thing. And we have this publicly and fixed gamma, and I'm just permuting the output of pi by gamma. We obviously know that this is true in the statistical setting, but now we know that it is true under I/O. Okay, so this kind of guarantee actually gives us the ability to obfuscate permutable PRPs. And just for the usefulness of it, we show that if you're using permutable PRPs, then it gives you the following theorem, that if you have one-way functions and I/O, both of them need to be sub-exponentially secure, you can construct a trapdoor permutation with the domain, with the densest domain, with domain 0, 1 to the n. Yeah, and I would like to conclude with two open problems. So what classes of permutations gamma can we permute by? I didn't say this, but we are able to do this indistinguishability only for gammas that we define in the paper are decomposable. So it's a definition, and once you have a gamma that answers this definition, you have this indistinguishability. So this is a purely combinatorial question. So every time that you show that a new gamma is decomposable, you have this indistinguishability. And we did not manage to show that all efficiently computable gammas are decomposable. So finding new families that are like this is one thing. Yeah, and the last one is something that I think that I'm answering this, that I'm asking this every lecture, and a lot of other people do, is can you have one-shot signatures or even public key quantum money, which seems to be way weaker without I/O. And yeah, with that, I'll end. Thanks.
Questions?
Sorry if I missed this. How can we conclude that J is well structured? Is it because it's like the map, or?
Yeah, you're talking about the last n/2 bits of pi, right? Sorry. Yeah, I mean, just because it's a permutation, right? So if I have any permutation and I'm measuring the first n over 2 bits and I'm looking on the remaining n over 2 bits, I have to go over all of them. And this is, what do you mean by well-structured?
I think at one point you mentioned that the assumption or assertion is that H is not well structured, but J was, or maybe I misheard.
Yeah, what I meant is that if I'm looking on the output of H, and then I'm looking on the pre-image set of that output, which is exactly this axis, if I'm considering only H, that's just going to be, by definition, a random 2 to the n over 2 to 1 function. So we know that this is just a random set of size 2 to the n over 2. So in this sense, it is unstructured, yeah. And then the J values take you to a structured set, which is the subspace.
We're out of time, so let's thank all the speakers of this session.